In this video we will finish section 14.3 and we'll deal with second order partial derivatives. Okay, so we still deal with the function z defined in two variables x and y. Z is equal to f of x and y, and we are looking for the second derivative with respect to x. So derivative with respect to x of the derivative with respect to x. So this is a much more common notation, okay? Also, partial derivative with respect to x of the partial derivative with respect to x, okay? Or this one is very common, second order partial derivative of f with respect to x. Or finally, if you use the name z for f, this is what you get. And similarly, for the rest of it, this is going to be second order, the derivative of a y of, so this is derivative with respect to y of the derivative with respect to y, or that's derivative with respect to y of the derivative with respect to y, right? Or something more used more often. Sorry, this is y, okay? Second order derivative with respect to y. So we usually use these notations. Okay, but now of course you can find the derivative with respect to x of the derivative with respect to y. So first you find the derivative with respect to y, and then that's gonna give you just another function as we saw in the previous video, and then you find the derivative with respect to x of this function. So this is equal to f. First you find the derivative with respect to y, then the second derivative with respect to x. But here you have to be a little bit careful. So now I'm looking for the partial derivative with respect to x of partial f partial y, which is written as the second order partial derivative of f, first in terms of y, then in terms of x. So be careful here, okay? First with respect to y, then with respect to x. And similarly, partial derivative with respect to y of the partial derivative with respect to x, that's partial derivative partial xy, which is equal to second order partial derivative first with respect to x, then with respect to y. Or okay. So let's do an example. Find the second partial derivative of the function f of xy defined as x cosine y plus y times e to power x. Okay, so obviously in order to get to the second partial derivative, I need to evaluate the first partial derivative. So partial f partial x is equal to, x is a variable, everything that doesn't depend on x is treated as a constant. Derivative of x is 1 times cosine of y, plus y is being treated as a constant, derivative of e to power x is just e to power x, okay? And now partial f partial y, by the same logic, it's negative x sine of y, x is being treated as a constant now, cosine of y, derivative of cosine of y is negative sine of y, plus e to power x is being treated as a constant, derivative of y is just 1. And now what does this mean? What is second order partial derivative with respect to x? That means I'm looking for the second order partial, I'm looking for the partial derivative with respect to x of partial f partial x. So that's of this function right here. Cosine of y plus y e to the power of x. Now in this expression here, in this function, right, only x appears only here. This is the function in terms of x. This is being treated as a constant. So cosine of y, derivative of cosine of y with respect to x is 0. Here y is treated as a constant. So that's y times derivative of e to power x is e to power x. Okay? Now, the second order partial derivative with respect to y is partial derivative in terms of y of partial f partial y, which is of negative x sine of y plus e to the power of x. When I differentiate this with respect to y, e to the power x is just a constant, derivative of constant is 0, derivative of sine of y is cosine of y, and here you have negative x stays because it's being treated as a constant. Okay? Now we'll see something interesting, and then we'll solidify that with a theorem. What will happen? Let's look at these mixed derivatives, right? So second order partial derivatives, first with respect to y, then with respect to x, which means the partial derivative with respect to x of partial f partial y, partial derivative with respect to x of partial f partial y is right here, negative x sine of y plus e to the power of x. Okay, sine of y here is being treated as a constant, so negative sine of y plus, because derivative of x is 1, plus e to the power of x. Okay, so this is, first I differentiated with respect to y, and then I found the derivative with respect to x of the derivative with respect to y. If I find the derivative, the mixed derivative fxy, that means that I'm looking for the partial derivative with respect to y of the partial derivative with respect to x, partial f partial x. So the partial derivative with respect to y of partial f partial x is right here, cosine of y plus y e to the power of x. If we differentiate this with respect to y, what do we get? Derivative of cosine of y is negative sine of y plus derivative of y is 1. E to the power x is being treated as a constant, so negative sine of y plus e to the power x. And now notice this part right here. Okay, so basically the second order mixed partial derivatives are always going to be the same, and this is being expressed by the Claros theorem. Suppose f is defined on a disk D that contains the point AB. Okay, so the point AB is in the domain of the function f of xy. If the second order mixed partial derivatives are defined, and continuous on the disk D, then these will give you the same value. Okay, so the second order partial derivatives, the second order mixed partial derivatives will always be the same. So let's show this through example. show that Clairaut's theorem holds for the function okay. So basically we want to show that fxy is equal to fyx, okay, that the two second order mixed partial derivatives are the same. Okay, so let's first find partial f partial x. Derivative of here I have to use the product rule, just to remind you. Derivative of x is 1, so ln of xy plus x times derivative of ln of u is 1 over u times u prime, so 1 over xy times derivative of xy with respect to x, that's only y, right? Derivative of x is 1, and this is being treated as a constant, and this is equal to ln of xy plus, here I cancel x and y, so plus 1. Okay, and the first order partial derivative with respect to y, partial f partial y is equal to, this is being treated as a constant, times, now the same logic, derivative of ln of u is 1 over u times u prime, so 1 over xy times derivative of xy with respect to y is just x. So I cancel these two, and partial f partial y is just x over y. Okay, so partial x partial y, that means that I have to find the derivative with respect to y of partial f partial x. Partial f partial x is right here, ln of xy plus 1. Derivative of a constant is 0. Derivative of ln of xy is 1 over xy times, by the chain rule, times x, which reduces to 1 over y. And partial yx is equal to the partial derivative with respect to x of partial f partial y. Partial f partial y is x over y. Okay, 1 over y is being treated as a constant. Derivative of x is 1, so 1 over y. And from here, we can see that Clairaut's theorem, of course, it holds. Okay. And then all of you that are going to go to study mechanical engineering for sure, and even electrical engineering, but I'm not sure, you'll definitely see a partial differential equation, and it's going to be one of the most difficult courses that you're going to take as the math part of your education. And partial differential equations are basically equations that contain an unknown multivariable function and its partial derivatives. Okay, so it's an equation between a multivariable function and its partial derivatives. One of the easiest, the most basic equations is called the Laplace equation. The Laplace equation is in 2 variables or in 3 variables. Okay, you can see this. You can see the Laplace equation playing a big role when you talk about fluid flow or electric potential or heat conduction and so on and so on. The solutions to these equations are called harmonic equations. So when you're gonna solve this equation, you'll get a multivariable function. That function is called a harmonic function. Okay, so here we're not going to learn how to find the solution of the Laplace equation, but rather we're just going to, as an example, we're going to show that the function e to power negative 2y cosine of 2x okay, is a solution to the Laplace equation. Okay, so basically I have to show this equality right here, okay, which is based on what? Finding the second order partial derivative with respect to x and y. So let's do that one more time. Partial f partial x is equal to e to power negative 2y. This one doesn't depend on x, so it's being treated as a constant. Times, this one depends on x, so derivative of cosine of 2x is negative sine of 2x times derivative of 2, which is, derivative of 2x, which is 2, so negative 2 e to power negative 2y sine of 2x. Partial f partial y, this here is a constant, right, because it doesn't depend on y, cosine of 2x, and here I have derivative of e to power negative 2y is e to power negative 2y times the derivative of negative 2y, that's negative 2, okay? Now let's find the second order partial derivatives. That's the partial derivative with respect to x of negative 2 e to power negative 2y sine of 2x, which is equal to, this here is a constant because it doesn't depend on x, right? So negative 2 e to power negative 2y times the derivative of sine of 2x, and that's cosine of 2x times the derivative of 2x times 2. So second order partial derivative with respect to x is negative 4 e to power negative 2y cosine of 2x. And then the second order partial derivative with respect to y is the partial derivative with respect to y of partial f partial y. Partial f partial y is right here, negative 2 e to power negative 2y cosine of 2x is equal to, these are the constants, so negative 2 cosine of 2x, and I'm just going to find the derivative of the part that depends on y, that's e to power negative 2y times the derivative of negative 2y, which is negative 2. So the second order partial derivative with respect to y is negative 2 times negative 2 is 4 times e to power 2y cosine of 2x. And obviously this is a harmonic function, or in other words, satisfies the Laplace equation.